All right, next up we have the replacement reactions, single and double replacement reactions. So again, I've written a generic equation here, so let's go through that first, and then we'll fill in the blanks. Some element A reacts with a compound in solution. So these reactions always occur in solution. So you have some compound in solution, By, and that reaction produces a different compound in solution, AY, and a different element, B. So notice what happened here. So A replaced B in the compounds. Let me show you that. Now, what types of things are going to trade places? So similar things trade places. So if A was a metal, let's say, A would replace the metal that's in the compound, By. Or if A was a nonmetal, then A replaces the nonmetal in the compound. So here's how it works. It says a reaction in which a free element, so that means an element by itself, replaces a less active element in a compound, setting the less active element free. So make a note in your notes anytime we are predicting the products of a single replacement reaction, we first need to see if that reaction will even occur or not. So to do that, we're going to use this table. It's called an activity series. And so we can see that activity decreases as you go down. We have two separate lists. We have metals on the left, and then we have halogens for halogen replacement reactions on the right. Here's how it works. An element can replace anything below it in this list. For example, what can lithium replace in a single replacement reaction? Go ahead and answer that. Now, I'm guessing some of you said potassium. Well, yeah, that is true. Lithium can replace everything there that's below it. Potassium, calcium, sodium, magnesium, all the way down to gold. So lithium can replace anything and everything that's on that list. How about gold? What can gold replace in a single replacement reaction? Go ahead and answer that. Gold cannot replace anything. So remember, those halogens are not underneath gold. They're their own separate list. So gold can't replace anything. What can platinum replace? Platinum can only replace gold. You may have noticed too in this list of metals that we have also hydrogen there. So some metals can replace hydrogen in an acid. I'll explain what that means later. And even the most reactive metals can replace hydrogen in water. So that hydrogen there is primarily for acids. We'll see examples of that in just a bit. And then on the other side, the halogens. What can fluorine replace in a single replacement reaction? Go ahead and answer that. Fluorine can replace chlorine, bromine, or iodine. What can iodine replace in a single replacement reaction? Iodine cannot replace anything. What can bromine replace? Bromine could only replace iodine in a single replacement reaction. So that's how we use that table. We'll be referring back to that anytime we have a single replacement reaction. So let's do this. How do you know, given the reactants, that you have a single replacement reaction? So you got to look at the reactants. We have an element reacting with a compound in solution. Anytime you have an element reacting with a compound in solution, that reaction is a single replacement reaction. By the way, if the reaction does not occur, please, please, please do not write a chemical equation. Chemical equations are meant to represent something that actually happens. So if no reaction occurs, write no reaction, or no NR, or no RXN. Either one of those is fine. All right, let's take a look at some examples. Write a balanced equation for the reaction between zinc metal and a solution of copper 2 chloride. So notice I'm changing the wording up a little bit, just abbreviated it in the notes. So reaction between zinc metal and a solution, aqueous, copper 2 chloride. So we are given the names of the reactants, so we'll start with those. Zinc and copper 2 chloride. Zinc is not diatomic, so it's just Zn. Copper 2 chloride, CuCl2. Okay, before we even attempt to write any products, let's go back to our activity series and see if this reaction can even occur or not. So the question is this: can zinc replace copper? So we're always looking at the element that's by itself. It's trying to replace something in the compound. Zinc is a metal, so that's why I said it's going to replace copper, or we're going to check to see. So similar things trade places in a single replacement reaction. So let's go back. So let's find zinc. Here's zinc on the list. Find copper. There's copper. Can zinc replace copper in a single replacement reaction? Yep, zinc can replace anything that's below it in the list. In this case, copper. So let me draw some arrows, show you what's going to happen here. With these, I think it's important to give the names of the products first and then write their formulas. So what do we make? So zinc goes with chloride to make zinc chloride, and then copper goes by itself. Now, is that 2 after chlorine because there was a 2 after chlorine in CuCl2? It is not. So those subscripts don't automatically transfer over to the products unless, there's only one exception to that, unless that subscript is part of the formula of a polyatomic ion. So why is it Cl2 and CuCl2? Well, it's because copper has a +2 charge. Why is it Cl2 and ZnCl2? Well, it's because zinc has a charge of +2. Has nothing to do with chlorine being diatomic. That's only when chlorine is by itself. So let's go ahead and put some states of matter. Zinc is a metal. And remember the wording I used. I said in a solution of copper 2 chloride. So copper 2 chloride is a solid that has been dissolved in water. You make zinc chloride. Is zinc soluble in water? Well, you'd have to check your solubility rules to see for sure. And yes, zinc chloride is soluble. It does dissolve in water. The water that was present before the reaction is still there after the reaction. Copper is a metal. Metals don't dissolve in water, so it's just a solid. And like always, we want to balance. In this case, everything is already balanced. So there you have it. All right, go ahead and try one on your own. Write the balanced equation for the reaction between sodium metal and magnesium bromide. Be sure to check the activity series and see if this reaction can occur or not. If not, don't write a chemical equation. Go ahead and pause the video and do that now. So checking the activity series, sodium can replace magnesium. So your products are sodium bromide and magnesium metal. Coefficients 2, 1, 2, 1. If you have it in this order, if you switch the magnesium and sodium bromide on the right side, that's fine, as long as they're both on the right side. Check to make sure your states of matter are also correct. All right, go ahead and try this one. Write a balanced equation for the reaction between fluorine gas, so fluorine is a gas, fluorine gas, and a solution of lithium chloride, aqueous lithium chloride. Go ahead and pause the video while you check to see first if this reaction will occur, and then write the equation if it does occur. Did you get this? Is this right, or did I write the wrong equation? First of all, can this reaction even occur, reaction between fluorine and lithium chloride? The answer is yes, it can. Now, did you do this? Did you switch fluorine and lithium? If so, that is not correct. Fluorine is a nonmetal. Better yet, it is a halogen. This is known as a halogen replacement reaction. So fluorine, the halogen, is going to replace which element in that compound? It's going to replace the nonmetal, or the halogen. So fluorine and chlorine trade places. You make lithium fluoride and chlorine gas. Make sure both your fluorine and your chlorine are diatomic, F2 and Cl2. And there is the balancing. All right, let's try another one. I'm going to walk you through this. This is a little bit different. Write the balance equation for the reaction between magnesium metal and a solution of hydrochloric acid. So this is a different type of single replacement reaction. This is known as a hydrogen displacement or hydrogen replacement reaction. You'll see why in just a second. So let's start off with our reactants. Hydrochloric acid is a commonly used acid in the laboratory. The chemical formula for hydrochloric acid is HCl. All right, here's how it works. In a reaction between a metal and an acid, the metal will replace the hydrogen in the acid. So what do you make? Give the names of the products first, and then we'll write their formulas. So magnesium goes with chlorine to make magnesium chloride, and then hydrogen goes by itself. Magnesium has a charge of +2. Chloride has a charge of -1. Hydrogen is by itself. Is hydrogen a diatomic molecule? Sure is. Next, states of matter. So this reaction will always produce hydrogen gas. And then go ahead and balance it. We need to balance the chlorines and the hydrogen. There you have it. Take a look at one that's kind of similar to that. So many metals will react with acids. In doing so, they will displace the hydrogen from the acid. The most reactive metals, do you remember where the most reactive metals are? They are the ones with the lowest ionization energies in their period. That's the alkali metals. The alkali metals, being so reactive, will even react with water. So they react with acids, but they can also react with water. And in the reaction between an alkali metal and water, the metal will replace one of the hydrogens in the water. So here's what I'm going to do. I'm going to rewrite water as HOH to make it a little bit more clear as to what is going on here. So the potassium is going to replace one of the hydrogens in the water. So potassium goes with hydroxide to make potassium hydroxide. And then we have hydrogen by itself. Hydrogen by itself is H2. All right, go ahead and pause the video, put in your states of matter, and balance. And there you have it. Remember to not leave water as HOH. Just helps us to predict the products for this one. Also helps us to balance. This reaction produces hydrogen gas, which of course we know is explosive. So this reaction is pretty violent because it produces a very flammable gas. All right, next up we have the double replacement reactions. So there's the generic equation. Some compound in solution AX reacts with a different compound in solution BY to produce two new compounds, AX and BY. So here's what's going on. A solution of an ionic compound is added to a solution of another ionic compound. The positive and negative ions switch partners, so A and B trade places, or likewise you can say X and Y trade places. It's one or the other. Don't switch them both because then you're going to end up with AX and BY on the right side as well. So cations trade places, or anions trade places, and one of three things will form in this type of reaction. A precipitate, which is an insoluble solid, a gas, and I'll show you which reactions produces gases, or water is produced. So let's start off with precipitation reactions, the formation of a precipitate. To determine which product is not soluble in water, we need to use the solubility rules. So make sure to memorize those. Again, those are on page 860 in your textbook. Memorize those so we know which product is our precipitate. Probably the hardest reactions for students to remember are the gas formation reactions, the double replacement reactions that lead to the formation of a gas. Now there's 4 possible gases that may form, and so you need to be on the lookout for these reactants. And so I'll go through each of them. There's 4, and I'll give you an example of the equation for these reactions. All right, first one. An ammonium-containing compound, so it doesn't matter what the anion is. It could be chloride, nitrate, sulfide, whatever. An ammonium-containing compound reacts with a hydroxide compound. For the hydroxide, I don't care what the cation is. It could be Li, Na, K, Ca. It doesn't really matter. So ammonium in one solution and hydroxide in the other solution. Let me show you how these react. Let's write an equation for this. So this reaction is going to produce 3 total products. I'm going to show 2 of them here. I'll give you some examples later, or I'll walk you through. So the ammonium ions in one solution react with hydroxides in the other to produce ammonia gas. So make a note, maybe in the margin, this reaction will always produce ammonia gas. It also produces water and another product, which comes from the cation of the hydroxide and the anion of the ammonium-containing compound. So this is the main things that react. All right, letter B. We'll start off with the gas, formation of carbon dioxide gas. Carbon dioxide gas is produced in the reaction between a carbonate, again, doesn't matter what the cation is, could be sodium, lithium, calcium, potassium, aluminum, doesn't matter. So carbonates and an acid. The acid will furnish the H plus ions, which are the other reactant in this reaction. So again, let's write an equation showing what happens. We have, again, 3 products that form. So carbonates react with acids. Technically, it's the H plus ion in the acid to produce carbon dioxide gas. Once again, water and another product. The other product comes from the cation from the carbonates and the anion from the acid. Next one, formation of sulfur dioxide gas. Sulfur dioxide gas. Sulfur dioxide is produced in the reaction between a sulfite and an acid. Sulfites with acids. Let's write the equation. So this reaction produces sulfur dioxide gas. Water and another product. All right, one more. A little bit different, so be careful this one. This one involves the formation of hydrogen sulfide gas. Hydrogen sulfide is the gas responsible for rotten egg smell. So sulfides react with acids to produce sulfur dioxide. Be careful this time, no water is produced. We have 2 total products. Again, the other product would contain the cation from the sulfide containing compound and the anion from the acid. All right, last one for double replacement, formation of water. Water is produced in the reaction between an acid and a base. An acid has H plus ions, a base has OH minus ions, and so these ions will combine to make water. This is also known as a neutralization reaction, acid-base or neutralization reaction. Let's take a look. So we get two products, one of them being water. The other product contains the cation from the base, the hydroxide compound, and the anion from the acid. So those will combine to make an ionic compound. So let's take a look at some examples of double replacement reactions. First one, write the balance equation for the reaction between a solution of silver nitrate and a solution of potassium chloride. So let's go ahead and write the formulas of the reactants. Go ahead and pause the video and do that. Now, something to be careful of that students will sometimes try is they'll use the activity series to predict if a double replacement reaction will occur or not. And we don't do that. The activity series is used only for single replacement reactions. So let's take a look at what happens. So silver and potassium are going to trade partners. Think about the names of the products. So potassium goes with nitrate to make potassium nitrate. Silver goes with chloride to make silver chloride. Let's go ahead and write those products. Now let's think about something here. Is this one of the gas formation reactions? So remember, 3 of the gas formation reactions involved a reaction with an acid. Neither one of these, silver nitrate nor potassium chloride, is an acid. The other involved a reaction with an ammonium compound and a base. No ammonium compound here, no base. Let's try neutralization. Is this a neutralization reaction? Nope, neither one of those is an acid or a base. So this must be the other one. This must be a precipitation reaction. So let's go ahead and put in our states of matter, but before we do that, we need to look at the products. One of those is not soluble in water. Take a look at your solubility rules and determine which one is insoluble, meaning it does not dissolve in water. Whichever one is insoluble in water, we'll put as a solid. Go ahead and pause the video and put in all these states of matter. So we see here that the silver chloride is insoluble in water. Most chlorides are soluble. There are a few exceptions. Silver is one of those exceptions, so it is our precipitate. Keep in mind, if you end up with everything being aqueous, that is not right. If everything is aqueous, that means no reaction occurred, and we're not going to see that in this class. All right, go ahead and do letter B on your own. Write the balance equation for the reaction between a solution of sodium sulfate and a solution of barium chloride. This is not a gas formation reaction, nor is this a neutralization reaction. Go ahead and pause the video, write the balance equation for this reaction. So according to the solubility rules, barium sulfate is not soluble in water, so that is our precipitate. Don't forget to balance the equation. Everything else in this reaction is aqueous or dissolved in water. All right, let's take a look at letter C. Write the balance equation for the reaction between a solution of hydrofluoric acid. So I gave you the chemical formula of hydrochloric acid earlier. Hydrofluoric acid has a similar formula. And a solution of potassium hydroxide. Potassium hydroxide is a base. In fact, all metal hydroxides are bases. So this is a neutralization reaction. In case you didn't figure it out, the formula for hydrofluoric acid is HF. Go ahead and pause the video, write the balance equation for this reaction. Do that now. So let's take a look at this. The H and the OH combine to make water. And then what's left makes our other product. Make sure to put the formula of the cation first, so that's K plus, and then the anion F minus. The equation's balanced. Water in this reaction is a liquid. All right, try another one. Write the balance equation for the reaction between a solution of potassium sulfide and a solution of hydrobromic acid. So now that you know the formulas for hydrochloric and hydrofluoric acid, you should be able to figure out the formula for hydrobromic acid. See what you get. Pause the video, please. So even though we have hydrobromic acid involved in this reaction, this is not a neutralization reaction. It's only neutralization if an acid reacts with a base. Potassium sulfide is not a base. And so this is one of the gas formation reactions. We have a sulfide reacting with an acid. The gas that is produced is hydrogen sulfide. You get water, and then the other product in this case is potassium bromide. Next, write the balance equation for the reaction between a solution of sodium carbonate and a solution of nitric acid. Nitric acid has a chemical formula of HNO3. Go ahead and pause and write the balance equation for this reaction. We have a carbonate reacting with an acid. This is a gas formation reaction. The gas produced this time is carbon dioxide. All right, one more. Balance equation for the reaction between solutions of ammonium chloride and lithium hydroxide. Go ahead and pause the video. Another example of a gas formation reaction. We have an ammonium-containing compound reacting with the base. That's always going to produce ammonia gas and water, and then the other product this time is lithium chloride. All right, that concludes the single and double replacement reactions. Thanks for watching.